Hello, my name is Dan, and I'm here to make another video to help you guys with studying alcohols. I'm just going to be going over all the new reagents and reactions, and hopefully you guys will find it as a useful resource to aid with your studying. So on this slide, I've gone ahead and categorized all of the types of alcohols, or alcohol reactions that you will learn in this section. First, reactions that make alcohols. Second, reactions that oxidize alcohols, and third, reactions that substitute alcohols. Reactions that make alcohols will typically create alcohols either through reacting with alkenes or using ketones, aldehydes, or esters and protonate them directly. Oxidation reactions are reactions where alcohols get turned into ketones, aldehydes, and sometimes even carboxylic acids by taking away their hydrogens and turning them into double bonds. And finally, substitution reactions will substitute alcohols for another group, and usually these are halide anions, but in this section we will learn about a new type of anion called tosylate anions, which will help us create even more substitution reactions. For our first type of alcohol reaction, we have reactions that make alcohols. We have already learned two reagents that help make alcohols, and these are oxymercuration and hydroboration. These reagents add an alcohol to alkenes, either on the most or least substituted carbon. In this video, I will just be going over the new reagents that create alcohols, so make sure to look back at your notes if you're unfamiliar with these previous reagents. The new reagents that create alcohols are lithium aluminum hydride and sodium borohydride. These reagents specifically target ketones, aldehydes, and esters and protonate them in order to make new alcohols. The biggest distinction between lithium aluminum hydride and sodium borohydride is that lithium aluminum hydride is more reactive than sodium borohydride. This means that lithium aluminum hydride will react with certain functional groups that sodium borohydride cannot, specifically esters. As you can see, both reactions will react with ketones and aldehydes, but only lithium aluminum hydride will react with esters, as you can see over here. Esters are more stable than ketones or aldehydes, so a more reactive reagent is needed in order to react with them, so we use lithium aluminum hydride. The reagents also need to reprotonate the functional groups in order to get an alcohol, and not just an oxygen with a negative charge on it. For the lithium aluminum hydride reagent, we use an acid workup step in order to get that extra hydrogen. And for the sodium borohydride, we use any protic solvent like ETOH. One of the many mechanisms that you will need to know for alcohols is the mechanism for lithium aluminum hydride. I won't be going over each step in the mechanism, but the key takeaways are that this reagent will always react to the less stable group first, and this almost always means that ketones or aldehydes will react first, and then esters if there is one present, such as in this case. So as you can see, the first step, the aluminum hydride reacts with the ketone first rather than the ester over here. Another key point is that if there is an ester, the reaction will cause an addition-elimination mechanism, which we can see down over here. This mechanism adds a hydrogen onto the ester, moving the electrons from the double bond to the oxygen like it normally does to ketones and aldehydes. But because of the extra oxygen on the ester, the electrons from the negatively charged oxygen go back and form a double bond to carbon again, and the electrons from the singular carbon-oxygen bond break away to the oxygen. So for our first step, we have the normal addition of hydrogen onto the carbon, which pushes up these electrons from the double bond to the oxygen. But then we have the elimination step, which the electrons from the negatively charged oxygen move down back onto the carbon, which forms a double bond over here. and pushes these electrons from the carbon-oxygen bond onto this oxygen. This breaks the bond between the carbon and the oxygen and leaves an extra negatively charged oxygen. And then the whole process repeats again, which leaves us with two negatively charged oxygen from one ester. This just goes to show how reactive this reagent is. And finally, we need to protonate all of the negatively charged oxygens, which will turn all of them into alcohols. It's definitely very helpful to get some practice and draw this mechanism for yourself, but these are just a few important moments that occur in this specific mechanism. Now we get to our second type of alcohol reaction, oxidation reactions. These reactions aim to make ketones, carboxylic acids, and aldehydes from alcohols, which is basically the opposite from the last type of alcohol reaction we went over. There are two new reagents we need to learn for these types of reactions: Na2Cr2O7 and PCC. Again, like the lithium aluminum hydride and sodium borohydride, there's one thing that distinguishes both of these reactions. Both reactions are able to react with primary and secondary alcohols to form the double bond. But only Na2Cr2O7 can react with a primary alcohol or aldehyde to create a carboxylic acid. This is because Na2Cr2O7 has water, and therefore will replace the extra hydrogen on secondary alcohols and aldehydes and replace them with an OH bond instead. PCC lacks the water in its reaction, so it will only create ketones and aldehydes from primary and secondary alcohols. Both reagents do not react on tertiary alcohols because those alcohols lack the necessary hydrogen atom that needs to be removed to form the carbon-oxygen double bond. Finally, we have our substitution reactions. We have done substitution reactions in the past, such as with HBr or HCl, which can react with alcohols using either SN1 or SN2, depending on whether the alcohol is primary or secondary. But we also are introduced to a couple of new reagents such as PBr3, SOCl2, and TSCl. Let's go over these new halide reagents first. These new reagents can react with both primary and secondary alcohols. The important thing here is that these reagents are able to perform SN2 reactions on secondary alcohols without any competition from SN1 or E2. This is because these reagents provide a good leaving group that pretty much guarantees an SN2 reaction, even on a secondary alcohol. It's not important to know the mechanisms for these reagents, but just know that they will do an SN2 on a secondary alcohol. Again, tertiary alcohols cannot react with these reagents because SN2 does not work on tertiary settings. For our last reagent, we have a new type of group called a tosylate. You can see the full structure of it over here, but usually it's abbreviated as just TS. The reagent TSCl lets us convert an alcohol into a tosylate group, as you can see over here. The reason why we sometimes might want to do this is that tosylate groups are a really good leaving group. We already know that water is a good leaving group, but water can only do so much. And usually it's only useful for things such as HBr, HCl, or H2SO4. But with an OTS group, we can do a lot of different types of substitution reactions, specifically SN2 reactions. If we look over here, we can see that one OTS group can perform SN2 to either create a nitrile, like over here, an alkyl bromide, or even an ether. If we can do SN2, tosylate groups will react with it. So that is it for our alcohol reactions. There's quite a bit of information and reagents that you will need to learn, so I suggest to work through these slowly and always refer to your resources whenever you get stuck. Hopefully this video is helpful in condensing all of this information and just as a quick review through each of them. Good luck and have a great